Hey there, in this video we're going to talk about Newton's law of cooling. And what it says is Newton's law of cooling states that the rate of change in temperature of an object is proportional to the temperature difference between the object and that of its surrounding environment, provided that the temperature difference is not too large. So imagine that you are baking a pizza or baking cookies so at 400 degrees in the oven. And then you take that out of the oven into a room that is say 70 degrees. So that's the surrounding environment. So that is going to affect how fast the pizza cools or cookies, right? So if you happen to be camping and you use a Dutch oven and the temperature outside says like 50 degrees, but the temperature inside the Dutch oven that you're making, say pizza or brownies or something while you're camping, then that could be anywhere from like 350 degrees to 400 degrees. Now, if you take that out and you put it in the 50-degree weather outside, that's going to cool a lot faster than the pizza or that you take out in a 70-degree weather inside a home. So that's what Newton's law of cooling is saying, that the rate of change in temperature of an object is proportional to the temperature difference between the object and that of its surroundings. And so from here we get a differential equation, which I'll give you a sneak peek. In calculus, you will solve this differential equation where T, big T sub s, is what we're calling the temperature of the surrounding environment. So after solving that differential equation, we see that the temperature of an object can be modeled by this equation. So when you are, like I said, when you get to calculus, you're going to be able to solve this differential equation up here to get this equation. So right now in pre-calculus, we're just going to take this equation as our model, where D naught, D0 here, is that temperature difference, the difference between the original temperature of the object and that of the surrounding environment. In case a positive constant that depends on the type of object, right? If you have pizza versus if you have soup versus if you have hot coffee, or the temperature of a person, the body, right? The normal temperature is 98.6 degrees for a human body. So depending on what kind of object you have, that D0 is going to change and the K is going to change. So let's try an example. So a hot bowl of soup with temperature of 210 degrees is served for dinner at 6 p.m. And then the soup cools according to Newton's law of cooling. The dining room has a temperature of 65 degrees Fahrenheit, and after 10 minutes, the soup has cooled to 150 degrees. If the optimal consumption temperature for hot liquids is 135 degrees, so that's when it's the sweet spot, right, to eat something or to drink something, how long will it take for the soup to be at that consumption temperature? So it comes out of the pot at 210 degrees Fahrenheit, and after 10 minutes it's at 153. So we want to know when will it reach 135 degrees. So we're going to use Newton's law of cooling formula to do this. So the formula is that T of T is T sub s, which that's the temperature of the surrounding environment, and D naught. So we need to find what all these values are. So I usually start with Ts, so the temperature of the surrounding environment. So what is my surrounding environment? Is the dining room. The dining room has a temperature of 65 degrees. So that's going to be 65 degrees Fahrenheit. And I also need to know, for my formula, I need to know what D naught is, that D is 0. So D naught is the temperature of the object, the initial temperature, minus the temperature of the surrounding environment. So the object in this case is the soup, and the soup came out with the original temperature of 210 degrees. So this is my initial temperature of the object. So this is going to be 210 degrees Fahrenheit minus that of the surrounding environment, 65 degrees Fahrenheit. So when you do 210 minus 65, you get 145 degrees. So we can change our equation to say, okay, so T of T is Ts, so 65, plus D naught. D naught, I just round it to be 145 e to the minus kt. So I don't know k. So we need to go back and read the problem and always focus on the question, what is it that we're being asked to do? So we're being asked to find, so where's the question? If the optimal consumption temperature for power glucose is 135 degrees, how long will it take? So how long does it measure of time? So I want to know time when something happens. For the soup to be at the consumption temperature. The consumption temperature is 135 degrees. So T, we're looking for T when the temperature of the object is 135 degrees. So that's what we want. But notice if I just put in 135 right now, I won't be able to solve for T because I have K. So let's go back and read the problem. What other piece of information do we have? And so hot bowl of soup with temperature to 10, blah, blah, blah. The soup cools according to Newton's law of cooling. Okay, so we have that up. So here's the piece of information we need after 10 minutes. So when T is 10, the soup has cooled to 153 degrees. So that's what we need to find K. And so just like we did with exponential growth and exponential decay, you could also do a table of values, right? So T, the time, and then the temperature of the object. So at time 0, the temperature of the soup was 210. After 10 minutes, the temperature of the soup is 153 degrees, and we don't know what time is going to be at 135 degrees. So the initial temperature helps me find my D naught. The second piece of information is going to help us find K. So I know then 153 is equal to 65 plus 145 e to the minus k times 10. Right? This tells me when T is 10, the temperature is 153. And we solve for K. So subtract 65 from both sides. So 153 minus 65, that would give us 88 equals 145 e to the minus k times 10. And so we want to solve for that k. So divide both sides by 145. So I have 88 over 145 equals e to the minus 10k. And I can use the definition of the logarithm. This is a log base. The base of my exponential is e, so I'm going to use a log base e, so the natural log. So natural log of 88 over 145 is going to be equal to just the exponent minus 10k, and now I can solve for k. So k is equal to the natural log of 88 over 145 divided by negative 10, which we said k should be positive because we already have a negative there. So we're looking, and that will be fine. Notice that 88 divided by 145, that's a number that's smaller than 1. So the natural log is going to be negative. Divided by a negative, I am going to get a positive number. How do I know that that's smaller, that that's going to be negative? Right, notice that, remember the graph of the logarithm of the natural log looks like that when you cross out 1. So anything that's smaller than 1, for any x's smaller than 1, the natural log is going to be down here in the negatives. So 88 over 145 is smaller than 1, so I know it's going to be a negative answer. So when you put that in a calculator, you get negative 0.04999. I get a lot of 9s in here. So this one I can actually nicely round it to 0.05. So I can do that because of all those 9s. If my digits were not as nice as this, not repeating, then I will probably leave it just as that quantity because I wouldn't want to lose significant digits. But here I can round it to negative 0.05. So now we have our equation. So T of T is going to be 65 plus 145 e to the minus k, which is found k to be negative 0.05 T. And so this is my equation. So now I can find T for a specific temperature. I can also find a specific temperature for a time. So if I want to know what about after 20 minutes, what's the temperature of the soup going to be, I can plug in T equals 20. For our case, we wanted to find when the temperature is 135, what's T? So this is what we're looking for. What is T equal to when the temperature is 135? So I'm going to go back over here and say 135, but the temperature is 65 plus 145 e to the minus 0.05 T. And now we can solve for T. So subtract 65 from both sides. So 135 minus 65, that gives us 70 is 145 e to the T. Divide both sides by 145, and then you can end up taking the natural log again. So e to the minus 0.05 T, converted to a logarithm, right? Base e, so there will be the natural log of 7 over 145 equals just the exponent, minus 0.05 T. And now we can get T out by itself. So T is this whole mess divided by negative 0.05. And so when we put this in a calculator, now T is time in minutes, so we should get a positive number, which again, notice 70 divided by 145, that's a number smaller than 1. So the ln of that is going to be negative. Divided by a negative, we're going to get positive, which is what we want. Time, you shouldn't get a negative answer for time. So when we put this in the calculator, I got that T is approximately 14.56. So this will be in minutes. So it will take about 14.56 minutes for the soup to reach 135 degrees Fahrenheit, a temperature that we can consume it. So you can either convert the 56, the 0.56 to seconds, by multiply the 0.56 times 60 to get how many seconds, or you can round it to 15 minutes. So kind of pay attention to what are you being asked to, how are you being asked to write your answers, in minutes and seconds, round to the nearest minute, or leave it as it is. So if you're asked to round to the nearest minute, it will be approximately 15 minutes. If you're asked to write it in minutes and seconds, 0.56 minutes, convert that to seconds, so it's a little over 30 seconds. So 14 minutes and 33 seconds is what it will take, approximately. So let's try another example. So this was Newton's law of cooling. So this is with just soup. So something's taken out of the, or it's served from the pot at 210. But you might see problems like this where a turkey is taken out of the oven, or a pizza is taken out of the oven and then placed in a room at a certain temperature, and then you apply Newton's law of cooling. Another application of Newton's law of cooling is in investigation, homicide investigation. So if anyone is going to be like a forensics scientist for police departments. So let's try this one. Time of death, right? So Newton's law of cooling is used in homicide investigations to determine the time of death. And as I mentioned earlier, the normal body temperature is 98.6. So immediately following death, the body begins to cool using Newton's law of cooling. And it has been determined experimentally, so by observing lots of bodies like this, then the Newton's law of cooling constant, K, is going to be 0.1947. So for this bowl of soup, right, we found our constant K to be 0.05. Whoops, that should have been positive. K is positive, we divided by a negative 10. Is when you put it in here, it has the negative. Okay, glad I went back to that. So we found the K to be 0.05. So that was for that particular bowl of soup. So if you take many bowls of soup, you might find that the K is approximately the same. So that's what has been done here. After observing lots of human bodies, then we determined that the constant K is 0.1947. And assuming the time is measured in hours this time, so let's always pay attention to our units. So we're measuring the time in hours. Suppose that the temperature of the surrounding is 60 degrees. Find a function t that models the temperature t hours after death. So we know, so for part A, we're going to use Newton's law of cooling. So that says T of t is the temperature of the surrounding, Ts plus d naught e to the minus kt. And remember, d naught is the original temperature minus the temperature of the surrounding environment. So this is the initial temperature of the object. So we know the temperature of the surrounding environment is 60 degrees. So this is going to be 60 plus d naught. So d naught, the temperature of a body, we know is 98.6 minus the temperature of the surrounding environment. So this will be 38.6. So plus 38.6 e to the minus k, we're given k as 0.1947. So that answers part A. We just want a function with the surrounding environment and the k figured out. So we've done that. Now part B says if the temperature of the body is now 72 degrees, so you're the forensic scientist that shows up at this scene and find a body in the temperature 72 degrees. So how long ago was the time of death? So, and again, focus on the question, how long ago? So we're looking for time. What is the time when the temperature was 72 degrees? So this was kind of nice because we were given the K, so we don't have to do that extra work in finding it. So we're just going to say 72, the temperature when the object was found, is equal to 60 plus 38.6 e to the minus 0.1947 t. We're looking for t. And solve. So 72 minus 60, right? We gotta undo this addition, so subtract the 60. So 12 is equal to 38.6 e to 197 t. And divide by 38.6. And then 12 over 38.6 equals e to the negative 0.19% t. Again, I have that exponential with an e, so we're going to convert it to a logarithm of base e. So that means the natural log. So natural log of 12 over 38.6 is equal to negative 0.1947 t. Again, t is time, so we should be getting a positive answer. So t is the natural log of this guy over negative 0.1947. Again, that's less than 1. 12 divided by 38.6. So the natural log of something smaller than 1 is negative. Divided by negative, you're going to get a positive. And this time, let's make sure that I actually do put the positive there. So do that on our calculator. And when I do it, I got positive 6.000. So that's pretty exact. So we can say t is 6 hours. So the time of death was approximately 6 hours ago. So since we're not given at what time the body was found, right? If it says something, the body at 6 p.m. was 72 degrees, then we would know, okay, well, if it was found at 6 p.m. with that temperature, then go 6 hours prior. And so the time of death would have been noon. But in this case, we weren't given a specific time, so we just say 6 hours ago. So that, hopefully that helps with Newton's law of cooling, understanding how it works. And the equation, when you get to calculus, you will get to solve this nice differential equation.